Okay, the next presentation will be on the process model of Torwash mild hydrothermal treatment, presented by Wilco Dijkstra. Wilco obtained a Master's in Chemical Reactor Engineering from the University of Twente and a professional doctorate in engineering from the University of Delft. He's now a scientist at FQ Project Coordinators TNO, and currently his research is focused on biomass conversion and valorization. Wilco, can you hear me?
Yes, I can. Can you hear me?
Yes, we can hear you fine. The floor is yours.
Should I share my screen, or can I just use your tab? How does it work?
No, share your screen.
I'm sharing my screen right now.
And we can see your presentation. Yeah, that's great.
Okay. Okay, thank you very much. Unfortunately, I can't be there in Florence, beautiful city, but presenting from home. So I'll be presenting the process modeling and system design for the F-Cube system. The work has all been performed by Wilco Dijkstra, but I've been closely involved and I will present. So this talk will be about the process modeling of the Torwash system itself. And in process modeling, lots of things come together. So you have the feedstock characteristics from lab analysis. We have the results from the experiments, all the unit operations, so the Torwash system, the filtration, the anaerobic digestion. And that we put all in a process model to obtain the mass and energy balances and to develop a conceptual process design. So what does the configuration look like and how do these different steps in the system interact? And that allows us then to assess the process in terms of, for example, energy efficiency and biopellet quality. So for modeling, we considered various approaches. So in the past, we have mostly used spreadsheet models, which are quite handy because you can customize them to match to your experiments directly. But downside is that they offer very little knowledge about integration of various process steps. That's quite complex to do that, and also not very flexible. So to go to more integrated models and more flexible models, we would need flowsheet modeling. And there are two approaches there. One is the biorefinery type of modeling, in which you address the composition of the biomass in terms of lignin content, glucan, xylem, ash, etc. There you can do the integration, and there's significant predictive value if you know the kinetics well, if you have a lot of experimental data. But the type of analysis we did in the project doesn't really align with that. And therefore, we chose the third option. That's the flow sheeting approach with thermal conversion type models. And there we characterize our flows in terms of carbon content, hydrogen content, oxygen, ash, etc. And these align directly with our experiments. And so you have the process integration option, and you have a direct connection with the experimental work. Flowsheet modeling uses streams and unit operations. And first step was to consider how to describe the streams in the process. And there we decided to use two substreams. So we discriminate between the dry matter content and the liquid content. And the dry matter is then built up of various components. So the main important one is the bioorganics, which is characterized by a virtual bio molecule, CXHYOZ, nitrogen and ash. And the ash is then again contains the phosphorus, the potassium, the sulfur, the calcium, the rest ash. The liquids, we have the same approach. I didn't show that. And to enter then in the flow sheeting software, we need to define components, real life components. So we make the selection there. For example, calcium, we entered as calcium carbonate. That was the streams, and then there's the unit operations. I will describe how we did that for the three main ones. So one is the Torwash unit, and there we have reactions going on. And the reactions, and we define it as one simple reaction. That's bioorganics plus the sulfur. So that's part of the bioorganics, but we modeled that separately, going to an upgraded bioorganics molecule and carbon, water, and H2S. And then these molecules are characterized by a molecular formula, and the composition of the molecules, so the X, the Y, and the Z, and also after reaction, the X, Y, Z accent, are taken from either lab experiments or from pilot experiments. So with quite a simple lab experiment, we could hopefully predict the working of the Torwash system for the large-scale applications. For anaerobic digestion, we used the experimental data for an anaerobic digestibility, and then the digestion of the biomass that is converted is modeled with the Bushwell equation, a well-known equation that gives how much methane you get from biomass. And the filtration, we use standard models, and the main assumption there is that the the solids are fully separated. So there's no solids anymore in the liquid stream, and then the filtrate contains both a liquid part and a solid part, and these both have their own composition. And this makes that we can predict how things change if the liquid content of the solids filtrate or the solids residue changes. If you're interested, we have submitted a paper, and these will give much more details on the modeling approach and the results. So far for the modeling, then on how this was implemented into a full-scale process. So this is the FQ process block scheme that has been shown a few times again, and this is what we entered in a model. So we have a preconditioning step, we have a Torwash unit step, we have dewatering, then we have the filtrate, which is sent to anaerobic digestion, and then we have biogas, which we can send either to a boiler or a gas engine, and we have pelletization, and the pellets go to into biopellets, and that can be combusted in an industrial boiler. Let's see. Maybe I have a laser pointer now. So this block scheme using the model was further developed, and then all the additional steps come into account. So then we have to specify for the paper sludge, first that we needed a decanter centrifuge to concentrate. Then we have the heat exchange steps, a preheater, we have the reaction step itself, and we have a gas which we need to clean in order to reduce the H2S emissions. So there we use iron sponge absorption. And after that, we have the filter press, we have to cool, we have an anaerobic digestion reactor, and we have a gas boiler to combust. The pellets are sent to a belt dryer, we crush it, we have to stabilize it, the ham is reduced in size in a hammer mill, and we send it to the pellet mill. And then after cooling, we have the biopellets. So all these steps have been implemented in the model. Then for the olive pomace and the orange peels, the system looks a little bit different. So I highlighted the differences only. So instead of a concentration step, we have here a dilution step. In order to feed, we need to add some water. Otherwise, the feedability is not good enough. And instead of having a boiler, we have here a gas engine that produces power rather than heat, because of the local demand of electricity and heat is different for the industries considered. For the rest, the system looks the same. We also defined several performance indicators to assess the process. So we have the biopellet quality. There we have an international standard. And we have the energy efficiency. And for energy efficiency, there are various options there. And I will be presenting two definitions of the energy efficiency. The first one is the energy efficiency towards the biopellets only. So how much biopellets do I get per amount of feed biomass? And there's the complex efficiency, and that considers all input-output streams. So also what comes from the biogas production, and it is also primary energy based. So we, in the end, we assess how much and the primary energy we will save implementing this process. I will be presenting several scenarios and cases. So we have the three feedstocks. That's paper biosludge, olive pomace, and orange peels. And there we compare the F-cube system with a reference system. And the reference system is anaerobic digestion of the feedstock only. So it's just an anaerobic digester being fed, for example, with olive pomace. And there we lose literature data for the anaerobic digestibility. And now presenting three cases. So that's modeling using lab experiments, lab experiment data, pilot experiment data, and we also have a custom case which is optimized after looking at the first iteration results. So for biopellet quality, we saw that the model is very capable of predicting the biopellet quality. Also is in reasonable accordance with experimental results. At the beginning of the project, we had set ourselves some targets, and later in the project, we also considered comparing to industrial standards for premium wood pellets. So that's the EN Plus standard for biopellets. And then the results are that in the table down the right, and the colors indicate to which extent we comply with the EN Plus standard. And there we see that if we use paper biosludge as a feed, we cannot meet the standard results. That's because of just the nature of the feedstock. If you look at the olive pomace and the orange peels, we don't totally meet it, but we are closing in, and maybe with a few adaptations of the process and optimization, we can even meet those standards. Anyhow, we can use these pellets in power plants or in the steel industry. Well, this is then the process efficiency, and as I said, the process efficiency is defined as how much energy is contained in the pellets, how much energy is contained in the feed, and then the feed is on a dry basis then. And then we have here with the three scenarios of the feedstocks, and then for the lab case LB, and for the pilot case data PL. And we see that the lowest is for paper biosludge. This is because a lot of organics go into solution, so we have little in our relatively little in our biopellets contained. The other pomace is much better. We have a little bit lower performance on the pilot plant case, and the orange peels is best. But if we go to the pilot case, it's much worse. And we think there's a lot of room for optimization still for the orange peels, especially in the Torwash process itself. These differences are quite large, but I must stress that if we have a lot of organic matter going into solution, this can be utilized in the anaerobic digestion, and this will then end up if we look at the complex efficiency. So this is the complex efficiency, and there we look at all outputs, input and output streams. So that's both for the biopellets as well as the energy we get from the anaerobic digestion in the system. And here we compare for paper biosludge four scenarios. So one is the reference scenario, so only anaerobic digestion of the paper sludge feed. Then the lab case and the pilot case, and then that is a little bit worse. But if we look then at the custom case, this is much better than the reference scenario. And in the custom case, we omitted the drying and pelletization step, and we just combust wet cakes on site. And we have a boiler there that is capable of combusting these wet cakes. And we think that is the best solution for this system. Then for olive palmas, we see that both the lab case as well as the pilot case are much better than the reference scenario with anaerobic digestion only. And it's quite a good efficiency if we look at these results. For the orange peels, we see a large difference between the reference scenario and the F-cube cases. But that is mostly due to the very poor performance of the reference scenario. And there we think that what is the case in the reference scenario, that we have a very low anaerobic digestibility because of inhibition by limonene in the process. And we don't see that in the anaerobic digestibility of the Torwash effluent. So this is why it is much better next to having the energy from the biopellets combustion. We do see that we have a little bit lower performance in the pilot case, and but the difference is much less than in the simple efficiency, and this is because we use a lot of the biomass that goes into solution in the anaerobic digestion. So the conclusion is that we have a flexible process model that is able to translate directly our experimental results into a system performance. The model gives all the data of all the streams and also allows for calculating the process efficiency. What we did find is that the most relevant model parameters are the amount of organics going into solution in the Torwash step, and we see that there's a large effect of the pellet moisture content. This is mostly why the pilot scenarios is worse than the lab scenarios, because the moisture content of the pellets produced in the pilot plant was higher. In the lab, we were able to dewater much more severely and have a lower water content of the pellets. The model allows for biopellet quality assessments. Currently, we see that the pellets are best suited for the power plant and steel industry, but we think we could further optimize and even then comply with the industrial standards for premium wood pellets. We see that for all feedstocks, the F-cube system is more efficient than the reference scenario, and but it's important there to take the anaerobic digestion step into account. Finally, the best scenario is the one with the paper biosludge with combustion of the wet cakes, which is much more efficient than the reference scenario, and which will also lead to cost reductions. And this concludes my talk.
Thank you, Jan Wilco. Any questions from the floor? Okay. We have a question online, Jan Wilco, just relating to your results and in terms of economic feasibility for the process. I mean, you mentioned the custom case of the paper biosludge, being most efficient in terms of, or most economically viable in terms of incinerating the wet cakes directly on site. Yeah, what about other parts of the process or the process in general in terms of economic feasibility?
Yeah, so we also looked at the economics, and we see there that the operating hours are key to having a profitable process. So a high number of operating hours is very important. And then we see that the paper sludge case is very attractive because that runs year round as a let's say, opposed to the seasonable availability of the feedstock for the olive pomace and orange peels. And diversification of feedstock there we find is very important. Also, we find that it's very important to have let's say, a burden on your feedstock, so a negative value. We see that the income from the biopellets is limited and cannot fully pay for the process. So having some additional income, let's say, from negative value of your feedstock would be very welcome.
Okay, thank you very much.